Okie dokie. I think hopefully we've gone live. Welcome everybody. Hello, hello, hello. Hopefully you can see and hear me. Oh, I don't think you can see my screen though. Let me just see if I can sort out my screen. But welcome everybody. Welcome to our A-level chemistry web class on calculating reacting masses. I'm just gonna, for some reason, they put the screen on the wrong one, so we'll just swap that over. But hello, welcome. If you're here, please feel free to say hi. It's lovely to know who we've got here. If you're returning somebody, or if you are if this is your first time at one of our web classes, then you're equally welcome. So lovely to have you here. Again, please feel free to say hi in the chat. We'll give it a couple of minutes just for people to turn up in case they're running late or whatever. And in the meantime, if you haven't already, please do download today's slides. They should be in the description below. So get them in front of you. That means you can write all over them. You can leave them and use them for revision later on. You can do both. You could save an unannotated version and then you could annotate, scribble all over one today, and then you can use the second version for revision if you so choose. But yes, it'd be lovely to know who's here. Please feel free to say hi in the chat, unless you don't want to, of course. But I think I saw one name that I recognised from previous classes. So yeah, do feel free to say hi. Oh, hi Marianne, how are you doing? I definitely recognise your name. How are things? Isn't results day coming up? I'm sure results day is soon. But hello, nice to have you here. Oh, you're waiting for results. Okay, fine, cool. I got excited then. But welcome. So this is this is an A-level chemistry class that we're doing on YouTube. So we do ones every month, approximately every month on YouTube. Oh gosh, yeah, balancing school with UCAT. Oh, that's not fun. Not fun at all. Definitely not. But nice, Mohammed. Lovely to have you here. Glad that you're doing well. We'll just give another maybe minute just in case anybody is going to join us, and then we'll get started. You've got an exam in October. Oh dear. Is that the UCAT exam, did you say? Or, oh, I'm just moving everything apparently. Try not to press too many buttons. My camera's just shifting slightly for some reason. There we go. Expecting to go through cleaning. Oh no, really? Well, if that's an expectation, that's a good expectation to have, because you can go into it with ideas of where you might want to go, places you might want to look at, you know, all that sort of thing. So yeah, definitely, at least you never know, because even if, and I think I've said this to you, to people before, but even if you don't get the results that you want, it's always worth contacting your first choice university and saying, look, I know I didn't get these results, but I still want to come here. You know, is there anything I can do? Is it possible for you to still offer me a place? Yeah, exactly. Mohammed, oh, okay. Oh gosh, well, good luck for that. Hopefully that goes well. Hello, Slim3, nice to have you here as well. I think we'll get started in just 2 ticks. Just gonna rearrange that cable so I don't pull everything off my screen. Oh, nearly did anyway. Lovely. Okay, right, I think we should get started. So welcome those of you who are new. I have seen some new names, I think, in the chat. So welcome everybody who is new. Lovely to have you here. These are our YouTube classes. So we run a YouTube class every month in biology, chemistry, physics, and maths. So always worth looking up these. It's also worth, if you haven't already, going back through our archives, if you haven't, to see our old classes as well. Lovely, Marianne. Lovely to hear from you as well. Thank you. Nice to see you. And hopefully I'll have all my fingers and toes crossed for you. Fingers crossed. Through our archives, we've got lots of other web classes that have been saved on the YouTube channel. So please do that as well. And if you haven't, I've already said this, but if you haven't already, please download the slides. They're in the description below. So they're very useful for revision, very useful for taking notes now. Extremely useful, and you should be able to find them from all of the other web classes as well, or YouTube classes, sorry, as well. Okay, right, so this is our web class on calculating reacting masses. This is a topic which technically is done at GCSE, but we actually do find that students find it quite difficult, and at A level you have to take it kind of one step further, or you're expected to do much more complicated questions. So it's very important that we get good at these and practice a variety of different reacting mass calculations. So let's have a look. So really briefly, I'm Alyssa. I'm the lead chemistry teacher at SnapProvise. I have a PGCE in chemistry education from Oxford University, as well as a master's in chemistry from Southampton. And I've been teaching science and A-level chemistry for the last 7 years. So I do love me some chemistry. So objectives for today, for the next kind of 50 minutes or so, we're going to recall the formula linking moles, concentration and volume. This hopefully you know from GCSE, but you may not. Then we're going to perform some calculations using that formula. And we're going to perform some calculations using the mass formula as well and link it with concentrations. So that tends to be the bit that students tend to find harder, is the fact that you've got to use two different equations in order to get to an answer. We're not going to look at ideal gas. That is an entirely separate web class. So we're not going to look at ideal gas today. Okay, so these web classes are geared for all three specifications, AQA, or three of the main specifications, I should say, AQA, OCR, and EdXL. So have a look at your specification points, the ones that we're going to cover. Not happy with, let me know and we can chat through it. So these are the specification points for AQA that we're going to be covering. These are the specification points for OCR that we're going to be covering. Apart from the ideal gas, we're not going to be covering ideal gas. And this is EdXL that we're going to be covering. Again, we're not going to be looking at ideal gas, so that's gases, not those two. Oh, my pen's being funny again. Gases. Okie dokie. So what do we already know? Let's work out what we already know. What is a mole? Does anybody know what a mole is? Pop it in the chat if you do know a definition, or if you can describe this funnily abstract concept of a mole. What is it? What is a mole? And why have I mentioned it? What's it doing in our web class? Does anybody know? If you do, pop it in the chat. What is a mole? Feels like an abstract concept, but it's just the same as by saying something like, if I say a dozen, or if you're Cockney, a score, or a pony, or a pair, a couple of something. It's just a way of determining an amount of substance. Lovely, T-Mackie, brilliant. That is exactly right. So it's, rather than saying a dozen is 12 of something, I could say 12, or I can say a dozen. I'll have a dozen of those, or there are a dozen of those. I can say there is a mole of those, and a mole is exactly right. 6.022 times 10 to the 23 objects, species, things. Species as in things. Oh, there's supposed to be an SS. Species, things. So a mole is an amount of substance that has that many Avogadro's number of things. So it's an amount of substance that contains Avogadro's constant, which is that value up there, of particles, or number of particles. once we've gotten our head around that concept, it makes a lot of our calculations and stuff a lot easier. Oh, yes, what you're thinking of there, Team Akid, that's a very good thing to remember, but that's not the definition of a mole. That's the definition of relative atomic mass, that it's the mass of an atom relative to 1/12 the mass of carbon-12. I think is what you're thinking of, which is a very good definition to have, but that's relative atomic mass. Yeah, so it's a good thing to have in your head for relative atomic mass. Yeah. Okay, let's do some super quick conversions. How do we convert 1 decimeter cubed into centimeters cubed? How many centimeters cubed are 1 decimeter cubed? Do we know? How many 1 decimeter cubed is equal to how many centimeters cubed? What's the conversion? And if we're not sure, think about what those terms mean. Deci meaning 10, so a decimeter, a tenth of a meter. So 1 decimeter, 1/10 of a meter in centimeters, must be 10 centimeters. If 1 decimeter is 10 centimeters, good, Navindu, very nice. Then 1 decimeter cubed must be the same as 1,000 centimeters cubed, because to go from decimeters to centimeters we times by 10, not times by 0, times by 10. So to go from decimeters cubed to centimeters cubed, we must times by 10 cubed, which is 1,000, so times by 1,000. Very nice. So therefore, if we know that 1 decimeter is equal to 1,000 centimeters, how much or how many liters is 1 decimeter? If we know that 1 decimeter is cubed is equal to 1,000 centimeters cubed, how many liters is that? Yeah, 1. Well done. 1 liter. Brilliant. Well done, guys. Fantastic. Because 1,000 centimeters cubed, 1 centimeter cubed is equal to 1 milliliter. So 1,000 centimeters cubed must be equal to 1,000 milliliters. And 1,000 milliliters is equal to 1 liter. Really nice. Very nice. Well done. Okay. Finally, this term molar mass is one that I will try to use mostly. Instead of using terms like relative atomic mass or molecular mass or things like that, I'm going to try to use this term molar mass because it is more of a catch-all kind of a general term, which is much better to use because then we don't make any mistakes with the terms that we're using. So molar mass, I'm going to use a fair amount. What do I mean by molar mass? What's the definition of molar mass? What's the definition of molar mass? Do we know? What's the definition of molar mass? Think about breaking it down. It's molar mass. So it's the mass of, it is MR, so we can use MR to represent it. Be careful because sometimes we use, or some people, some teachers, some textbooks, etc., use MR as relative molecular mass. So also some relative molecular mass is sometimes written as RMM. So there is an interchange. People do use the term interchangeably, so just be careful. But molar mass is exactly right, the mass of 1 mole of a substance. Exactly right. The mass of 1 mole of a substance. It's the molar mass, the mass of 1 mole. Very nice. Okay. Fantastic. Let's whiz on then. So what's this equation then? This elusive equation, which we need to have drilled into our head, and it needs to come super, super quickly to us. So if you haven't learned it yet, get it stuck on a piece of paper on your wall or in the bathroom or next to the kettle, so that whenever you're doing something, you can be checking that you know this equation off by heart. So the mass, concentration, and volume if you're somebody who likes to use equation triangles, then we've got a version of the equation triangle here. If you're somebody who prefers to use just an equation, then any one of the equations will do, but often moles equals conc times volume in decimeters cubed is one that we can remember. Moles equals conc times volume. Sometimes people remember it as N equals CV. That's quite easy to remember. So if that's you, that's absolutely fine. But we have to make sure that our volume is in decimeters cubed because concentration is in moles per decimeter cubed. So we do need to have our volume in decimeters. Okay, anybody got an answer for this question that's on the page then? Calculate the number of moles of HCl in 50 centimeters cubed of a 5 mole per decimeter cubed solution. How many moles of HCl are there in 50 centimeters cubed of a 5 mole per decimeter cubed solution? You might need to get a calculator out if you've got a calculator. Yeah, Rishu, you're absolutely right. A mass of 1 mole of an element is its molar mass. That's exactly right. Oh, yeah, looks good, Timaki. Let's just double check. So the thing we might have noticed, I did put a little bit of emphasis on it, but this is often the bit that students make mistakes on in exams. And if it's only a 1-mark question, then you've lost the whole mark, which is a shame. If it's a 2-mark question, you may only lose 1 mark, which would be good, but we do have to make sure that we put our units in the same unit. So first of all, let's convert our volume. So we've got 50 centimeters cubed. Before we look, how do we convert decimeters to centimeters was times 1,000. So to go the other way, centimeter cubed to decimeters cubed, we need to divide by 1,000. So that means we should have 0.05 decimeters cubed. Yep, just checking that one. So our volume needs to be in decimeters cubed. And then we can just plug it straight into our equation. So moles equals concentration times volume if we're using the equation triangle. Moles equals concentration times volume. So N equals, or if you want to, N equals CV. Moles equals concentration times volume. Our concentration is 5 mole per decimeter cubed. And our volume is, oh no, I nearly put the wrong one in, 0.05 decimeters cubed. That means our per decimeters cubed and our decimeters cubed cancel, and we're left with just a moles. So moles equals, absolutely right, 0.25 moles. Very nice, well done. If anyone's not happy with that, just make sure that you're happy with your using the equation triangle. It's really important that you're happy with how to do an equation triangle. And we also need to make sure that we're on it when we're doing our units. Okay, let's have a look at some more complicated ones, because this hopefully we're a bit more secure on. Let's have a look at some more complicated ones. Okay, so here we've got a question. We've been given an equation. It says KCl plus AgNO3 goes to make KNO3 plus AgCl. It says KCl reacts with a 3 mole per centimeter cubed solution of AgNO3. So that's AgNO3. Calculate the volume in decimeters cubed of silver nitrate solution. That's what we're looking for. Needed to react with 10 moles of KCl. Yes, I do the same, Rydal, exactly. Yeah, that's a very good idea. In my head, I have the divide by 1,000 already in the equation because we nearly always get given volumes in centimeters cubed. So absolutely, personally, I too have that drilled into my head. However, we do have to be super, super careful because sometimes they give us volumes in decimeters cubed. And then if we divide by 1,000 again, suddenly we're out and our units are wrong. So yes, I'm the same as you. Just be very aware when you come to a question. Anybody got an answer for this one? For this first one? We were trying to work out the volume of silver nitrate solution needed to react with 10 moles of KCl. What are we thinking? Anybody got any ideas? We've got 10 moles of KCl, just writing out the information that they've given us in the question. KCl reacts with a 3 mole per centimeter cubed solution of AgNO3. So our 3 mole per centimeter cubed of AgNO3. And we're trying to work out the volume of silver. That looks pretty good. Yeah. Oh, there's a very loud and low helicopter going past. Apologies if you can hear it. Oh, that's very low and loud. Apologies for that. Yeah, lovely. Good. Molar ratio, perfect. And then find our volume. Yep. And that looks like a good calculation as well. So let's just double check. We've got 1 lot of KCl react with 1 lot of silver nitrate. That gives us our 1:1 ratio. Therefore, if we had 10 moles of KCl, we must need 10 moles of AgNO3. So we know our molar amount now, and we've already been told our concentration, so we can just use those to find our volume. Perfect, really nice. So that means we're going to need to use a rearranged version of our equation. So we don't want to find moles this time, we want to find volume. So volume is equal to moles divided by concentration, and you can use the equation triangle if that's your thing, or you can rearrange a written equation, whichever suits you. So we've got a concentration. Our concentration, well, actually, let's just plug the numbers in. So we've got 10 moles divided by our concentration, which is 3 moles per centimeter cubed. What unit is our volume going to have in this case? What unit is our volume going to have? If I do 10 divided by 3, I'm going to get 3.3 recurring. What's the unit at the moment? If I do 10 moles divided by 3 moles per centimeter cubed. So the moles are going to cancel. I'm actually just going to be left with centimeters cubed. Now they've asked for a volume in decimeters cubed, and I see that Rydell's already converted it, which is fabulous. So we're going to go from centimeters cubed to decimeters cubed, which means divide by 1,000. So 3.3 centimeters cubed times 10 to the minus 3, or 0.12123, 0.003. So Rydell, just double check that you put your numbers in the right place, because I think it would be 0.003. So just double check that you're happy with that. Lovely. And then we've got our answer. Fantastic. Okie dokie, let me know if anyone's not happy with that. Otherwise, we'll move swiftly on to the next one. So our next one says we've got react together to form lead chloride and 2 lots of nitric acid. Here we've been told that 0.35 moles of lead nitrate reacts with 100 centimeters cubed of HCl. We have to calculate the concentration of HCl in moles per decimeter cubed. Okay. First things first, what can we do? What can we calculate? We know we've got 0.35 moles of lead nitrate. So how many moles, how do we work out the ratio with HCl? We need to find the molar ratio. That looks promising, Team Echo. Let's have a look. So it's a 1:2 ratio this time, a little bit more complicated. So if we've got 0.35 moles of our lead nitrate. That must mean yeah, good, well done. We must have of our HCl. It's got to be twice as many moles. Good, so it's times by 2, 1 to 2. Perfect. So that means we know we've got 0.7 moles of HCl. Brilliant. Oops, I forgot to put moles of HCl. Let's write moles in there. Mole of HCl. Then we're trying to find the concentration. So again, we're going to need a rearrangement of our equation, or if you're using an equation triangle, you can just use your equation triangle. So we've got concentration is equal to, as long as our volume is in decimeters cubed. So it needs to be, yeah, just double check your conversions, because we've got 100 centimeters cubed. So our volume needs to be divided by 1,000, or you can do the whole thing times by 1,000. It doesn't matter which way around you do it, as long as you do them together. As long as you do them in the right order. So we should get, where's my moles gone? 0.7 moles divided by our volume, which is 100 centimeters cubed over 1,000. So we should end up with, it looks promising, 7 mole per decimeter cubed, or 7 capital M. Capital M means moles per decimeter cubed. At A level, though, we should probably be looking to use the term mole per decimeter cubed, just so that, because we don't tend to use the capital M anymore. It's used in laboratories loads, but not at A level, not in our exams anyway. So really well done if you got that. That's brilliant. 7 moles per decimeter cubed, or mole per decimeter cubed. Okay, take a second just to think how confident you're feeling, and give me a 1 or a smiley face if you're feeling pretty confident about that so far. A 2 or a face if you're, it's all right, I guess I might need to practice it again. Or a 3 and a oh if you're feeling super confused about that. Lovely, that looks good. These are for you guys as well. It's really, really a good idea, if you haven't already been doing it, to take your time after every topic and every like test that you do, and consider how confident you're feeling about a topic, because then you can make a mental note or even a physical note if you need to, because I never remember anything, to say, oh, I need to come back to this topic, or no, I was feeling quite confident about this, I'll try it again in a month or so just to check. So really good idea. If you haven't already, download your specification and scribble all over it. Write these kind of notes all over it, because it will be super, super useful to you when you come to do your revision. Okay, let's have a go at this slightly horrible exam question, and then hopefully we'll have time to finish up with a couple more moles questions at the end, where we combine mass and concentration. Okay, so it looks like a horrible equation. Luckily for us, this question is talking us through it. So we've been told, luckily, which order to do it in. Not all exam boards do it like this. Sometimes they like to give you big kind of 5-marker questions. You've got to make your own way through it. Sometimes they like to talk you through it a bit. So let's just have a look at what information we've got here. I'm going to read it out, but obviously if you want to block your ears and read it yourself, then that's absolutely fine. So there's a lot of info. So a student was given 200 centimeters cubed of solution X. Oh, come on, pen. Oh, doesn't want to draw a full line there. Let's try that again. There we go. So a student was given 200 centimeters cubed of solution X, in which sodium hydroxide and sodium hydrogen carbonate, NaHCO3, were both added. They've both been dissolved. The student carries out 2 different titrations on samples of solution X using 1 mole per decimeter cubed sulfuric acid. In the first titration, both sodium hydroxide and sodium hydrogen carbonate were neutralized. In the second titration, only sodium hydroxide was neutralized. The student's results for the titrations of 25 centimeter cube samples of solution X are shown below. The volume of sulfuric acid needed to neutralize both of those salts, both of those bases, was 29.5 centimeters cubed. The volume of sulfuric acid needed to neutralize only sodium hydroxide was 18 centimeters cubed. We've also been given the equations for the reaction of sodium hydroxide with sulfuric acid and sodium hydrogen carbonate with sulfuric acid. Lot of info there. Let's see what we can do with it. The first question says, calculate the amount in moles of H2SO4 used to neutralize only the sodium hydroxide in the 25 centimeters cubed of solution X. So if I number my titrations 1 and 2, it says calculate the amount in moles of sulfuric acid used to neutralize only the sodium hydroxide. So which titration, or both, am I expecting to use here? Good, titration 2, because that's the one where it's only sodium hydroxide. Really nice, okay. So anybody got a value for me? Calculate the amount in moles of H2SO4 used to neutralize only the sodium hydroxide in 25 centimeters cubed. We need to use titration 2, very good. So if we use titration 2, that tells us that 18 centimeters cubed of our sulfuric acid was needed to neutralize the sodium hydroxide. And I'm trying to find out the amount in moles of H2SO4. Well, I know that I've got 18 centimeters cubed of H2SO4. What's the concentration of H2SO4? Well, I was actually given it above even. I was given it above. So this is, yeah, lovely. That looks good. This is a quote unquote simple calculation in that we're calculating moles. Moles are equal to concentration times volume, as long as volume is in decimeters cubed. So I might as well convert that straight to decimeters cubed. 1, 2, 3, yeah. So moles equals conc times volume. My concentration is 0.1 moles per decimeter cubed. My volume is 0.018 decimeters cubed. The decimeters will cancel, and I end up with, very nice, 1.8 times 10 to the minus 3 moles. Hopefully, I should do. (1.8 times 10 to the minus 3 moles. Let me know if anyone's not happy with any of those bits. Otherwise, it then says calculate the concentration in moles per decimeter cubed of sodium hydroxide in solution X. Yes, I can see that, but because this is telling us this is the volume of H2SO4, this is the volume of sulfuric acid. So we've been given a volume of sulfuric acid and we've got a concentration of sulfuric acid, and they want us to know the moles of sulfuric acid. We actually only need to use those values for sulfuric acid. You're very right in recognizing we might need to use the ratio, but not for the sulfuric acid, because it's all the information is just about sulfuric acid, so that's fine. This question is now asking us about the sodium hydroxide. Yes, yeah, good. So because this question is about sodium hydroxide, now, yeah, good, exactly. Now we need to think about our molar ratios. Very nice. So we've got two equations. Just make sure we use the right one. The first equation, I'm going to call that equation A so that I'm not naming it 1 and 2 again. So first time equation A, we've got 2 to 1. 2 lots of sodium hydroxide needed for 1 lot of H2SO4. Just double check you're happy it's 2 to 1. 2 lots of sodium hydroxide for every 1 lot of H2SO4. Because it's a 2 to 1 ratio, our moles of sodium hydroxide, if our moles, wait, let's do it up here actually. So sodium hydroxide to H2SO4 is 2 to 1. So if our moles of sodium hydroxide, moles of H2SO4 were 1.8 times 10 to the minus 3, we'll double check. So it would be 2 to 1 sodium hydroxide to sulfuric acid. So the moles of sodium hydroxide must be twice as big as the moles of H2SO4. H2SO4. And therefore, 2 lots of 1.8 times 10 to the minus 3. Let me know if anyone's not happy with that. Yeah, just double check that it's 2 to 1. Yeah. Otherwise, your process is correct. We just need to get the initial moles right first. So the moles are 3.6 times 10 to the minus 3, should be, times 10 to the minus 3 moles. And then which volume are we using? This is a big challenge sometimes. What volume are we using? If we're looking at sodium hydroxide, this amount, these moles of sodium hydroxide, is in what volume of sodium hydroxide? What's the volume of sodium hydroxide we're using? Because concentration is equal to moles divided by volume. I've got the moles of sodium hydroxide, but I now need to do the volume. Well done, Team Aku. Exactly right. It is 25. And that's where we often get stuck. We have to be so good at holding all of this information in our brain. And it's the 25 centimeters cubed, because it was 25 centimeters cubed of solution X. So when we put 25 centimeters cubed of solution X there must have been 3.6 times 10 to the minus 3 moles of sodium hydroxide in there. So 3.6 times 10 to the minus 3 divided by, now it's got to be in decimeters cubed, not centimeters cubed. So where is it? 0.025. Oops, running out of space. Decimeters cubed. So it's got to be in decimeters cubed, not centimeters cubed. It's all complicated, isn't it? So we should end up with a value of 0.144 moles per decimeter cubed. It's hard, that. It's very hard. Again, take a second just to think it through. Check that you're happy why we used each of these values, why we doubled it, why we used the 25 centimeters cubed or 0.025 decimeters cubed, and just check that you're happy with each of those. So we should end up with our moles being 3.6 times 10 to the minus 3 moles divided by 0.025 decimeters cubed. So just double check that we're happy with that. Finally, I'm just aware that the time is ticking on a little bit, so please feel free to ask any questions, but I'm just going to move on to the final bit, BI. It says calculate the amount in moles of sodium hydrogen carbonate in 200 centimeters cubed of solution X. So in the original 200 centimeters cubed. So now we've got a lot more calculations to do here. How are we meant to do this? How on earth are we meant to work out how much sodium hydrogen carbonate there was in the original 200 centimeters cubed? What can we use? Cool, good, well done. Well done, well done. That's a good thought. That's a good thought, but how do we know where, that's a very good thought. I like the fact that you're using the differences. If we did it in the 200 though, however, we wouldn't know how much to subtract. I think, because we haven't used it yet, so my guess, my educated opinion is that we're going to need to use titration number 1. This value here, I'm just writing in red to make it a bit clearer. This value here is how much sulfuric acid was needed to neutralize both sodium hydroxide and then sodium hydrogen carbonate. So what volume of sulfuric acid is needed to neutralize just the sodium hydrogen carbonate? What volume of sulfuric acid is needed to neutralize just the sodium hydrogen carbonate? We were told specifically that 18 centimeters cubed. Very nice. Yeah, brilliant, both of you, fantastic. Titration 2 is just sodium hydroxide. Titration 1 is both of them. So we can work out the difference. It tells us how much sodium hydrogen carbonate. Fabulous. So the volume, now your notes don't have to be quite as detailed as this, but I'm going to try to write down as much of it as possible. So the volume of H2SO4 to neutralize, I'm just going to write NaHCO3 is going to be, come on pen, you're being really slow, 29.5 minus 18, which absolutely right is 11.5 centimeters cubed. Very nice. Now we've basically done everything already. We know the process because we've literally just done it in parts A, I, and II. So hopefully, or at least most of it we've done, hopefully we should be able to whiz through this. So we've got our volume of sulfuric acid. We also know the concentration of sulfuric acid. So we should be able to work out how many moles of sulfuric acid was required to neutralize the sodium hydrogen carbonate. Our equation, if we can remember it, moles equals conc times volume, as long as volume is in decimeters cubed. So conc times volume in decimeters cubed. So that's 0.1, because again, that was given to us earlier in the question up there. 0.1 moles per decimeter cubed times by our volume, which is 11.5, but it needs to be in decimeters cubed, so we need to divide by 1,000. So hopefully, if I plug my numbers in correctly, my moles should be 1.15 times 10 to the minus 3 moles of sulfuric acid needed to neutralize the sodium hydrogen carbonate. Let me know again if we're not happy with that. So that's our sulfuric acid moles. I don't care as much about sulfuric acid moles. I'm more interested in the sodium hydrogen carbonate moles. So how do I work that out? Well, if I've got my moles of H2SO4, I can work out my moles of sodium hydrogen carbonate, because as before, it is a 2-to-1 molar ratio. Therefore, my moles of sodium hydrogen carbonate, and I'm just going to put a caveat, in 25 centimeters cubed, because it is only in 25 centimeters cubed, exactly right, we're using the molar ratio, is 2 lots of the moles of H2SO4. So 2 times 1 times 10 to the minus 3, because of the 2-to-1 molar ratio, which is, I can't do mental maths, 2.3 times 10 to the minus 3 moles of sodium hydrogen carbonate in 25 centimeters cubed. It wants it in 200 centimeters cubed. So how do I do that? If it's 2.3 times 10 to the minus 3 moles in 25 centimeters cubed, how do I convert it to 200 centimeters cubed? Good. You've obviously got some good mental maths going on. If I'm not sure, I can work out the conversion. How many times does 25 go into 200? Oops, wrong way around. How many times does 25 go into 200? Sorry, should be that way around. Is 8 times. So I must have 8 times as many moles in 200 So my moles of sodium hydrogen carbonate in 200 centimeters cubed. Oh, it's been really slow. Is 8 times 2.3 times 10 to the minus 3. Yes, good. Or you can use a 25 to 200 ratio. Yeah, that would work as well. And then we should have 0.0184 moles. Considering this is only 1, 2, 3, 4 marks, I think that's horrible. Just being honest. Considering that's only 4 marks, I think that is a horrible exam question. However, that's what we're expected to do. Let me know if there's any part of that which doesn't click as quickly. It must be AQA. Probably, I'm afraid. Probably. I think, unfortunately / fortunately, one of the reasons this is only worth so few marks, will be multiple reasons, but the main things will be some of these skills probably will have already been tested earlier in the exam paper. So they're not offering, for example, 2 marks for doing the molar ratio and the concentration calculation in part II, because maybe we'd already done that earlier on in the exam paper. But also because they're leading you through the question by telling you to do the amount of H2SO4, then work out the concentration of H2SO4, sodium hydroxide, sorry. That's leading you through the explanation, as it were, leading you through the answer a little bit. So I assume that must be why they feel they can offer so few marks for it, because they think they're giving you some hints with that. However, I still think it's horrible. But there we go. Now we've done it. So if we see another similar question, we can tackle it similarly. And having said that, I have seen a couple like this actually in past papers. So they do like to do questions like this where you've got 2 things going on and you've got to work out differences in moles and stuff. Okie dokie. Right. Let's move on to part 2. So how much time we've got? Oh, we've got 13 minutes. That's right. We can do it. So let's do some calculations using masses. This you might be more confident with, perhaps. It might be something maybe you did more at GCSE, or maybe you've done a bit more in your A levels. We just need to make sure that we're confident in combining the 2, really. So sometimes calculations are done where you're given mass in grams rather than moles. So we have to convert to moles before we can then convert to concentrations or things like that. So let's have a look at this one. Trilithium nitride and 3 lots of ammonium nitrate react together to form lithium nitrate and ammonium nitride. 100 grams of lithium nitride reacts with 300 centimeters cubed of ammonium nitrate. Calculate the concentration of ammonium nitrate in moles per decimeter cubed. So again, let's think about what information we've got. We've been given a mass of lithium nitride, and we've been given a volume. They want us to calculate the concentration. So we're going to need, yes, very good. Well done, Riadul. Exactly right. If we want to work out concentration, we need to know moles. So we're going to have to work out our number of moles. Brilliant. So moles, if we think back to our moles equation, so not the moles concentration volume equation, oh, hello, Mushafi, brilliant. Nice to have you here. Our other moles equation is mass divided by molar mass. Moles are equal to mass divided by molar mass. So first things first, we're going to need to work out our molar mass. What's the molar mass of lithium nitride? Has anybody got their periodic tables up next to them? What's the molar mass of lithium nitride? Because we know we've got 100 grams of it, and we need to divide it by its molar mass. What is its molar mass? I think lithium is 7, if I remember rightly. 7 point something. And then nitrogen is 14 point something. So 14.1 maybe. So what I've got written in front of me here is the molar mass of lithium, trilithium nitride is 34.7 grams per mole. If it's 34.7 grams per mole, then my moles of lithium nitride, or 35 if you round up, yeah, lovely. So my moles of lithium nitride is therefore 100 grams divided by 34.7 grams per mole. That means our grams cancel, our mole gets brought up to the top, we end up with moles. That's good, that's what we want. So 2.888 moles. Cool. If you just use, let me just, whoops, moving everything. Let me just get my calculator out. Just to double check, if we just use, yeah, so if we just use 7 and rather than 6 point something, whatever it is, we get 35. That's absolutely fine. Use whatever values are on your periodic table. So when you're given your data sheet in the exam, use the values that you're given because they may differ. Your exam paper might choose to give them to you in the question. Just use whatever you're given and then they can't mark you wrong. Obviously, unless you make a mistake, but I mean, the answer that you get using their values can't be marked as wrong. Okay, so then we've got 2.888 moles of trilithium nitride or lithium nitride. If we do it just so that we've got it, 100 divided by 35 is 2.857142 recurring, so 2.86 if you use the value 35 for the MR, 2.86. I'm going to use 2.88 because it's the value I've got in front of me. So that's our moles of lithium nitride. How many moles of ammonium nitrate do we have then? We've got 2.88 moles of lithium nitride. So how many moles of ammonium nitrate must we? Yeah, good. We need to use the molar ratio, which in this case is an interesting 1:3. Lovely. That looks good. Yeah, brilliant. Well done, all of you. That's fabulous. So our moles of NH4, NO3 have got to be 3 times as big. Fabulous. Well done. So 3 times. Again, use whichever value you've got in front of you. I'm going to use my 2.888, but you use 2.86 if you want to. So that gives me 8.64 moles approximately. Have I pressed? Hold on, let me. 2.888 times 3 to 8.664. Oh, that's interesting. I had a wrong value there. Well done. Ms. Shafi, looks like you've got it correct. So that's my moles of ammonium nitrate. I've got moles. I've got a volume. I need to find concentration. Concentration, let's just rearrange the equation in our head or use the equation triangle if we can. Concentration is equal to, you may already know the definition of concentration. The definition of concentration is moles per unit volume. So moles divided by volume. You may already know that off the top of your head. If you don't, that's absolutely fine. It's a nice way, I think, of remembering, of using the units. Concentration is equal to moles per decimeter cubed. So moles divided by volume. It's the way that I can tend or try to remember anyway. So moles divided by volume, you're absolutely right. So 8.664 divided by 300. Oh, they wanted the concentration in decimeters cubed. I'm in centimeters cubed, so I just need to convert to decimeters cubed by dividing by 1,000. If you haven't already, it looks like people have, so that's brilliant. And I should get 28.8 moles per decimeter cubed, and that's to 3 sig figs, because that's what they've asked for. Really nice. If you've got that, that's fabulous. Anybody not happy? Otherwise, hopefully we're all good. Let's super quick. We've only got 5 minutes, so and that means we're probably not going to have time to do the final question. So let's just see if we can whiz through this final bit here. So sodium carbonate is added to potassium fluoride, and it gives us sodium fluoride and potassium carbonate. 0.81 mole per decimeter cubed sodium carbonate reacts with 12 grams of potassium fluoride. Yeah, I know what you mean. They are tiring, and I don't know about you, but they do get a little bit like repetitive sometimes. But that's why if you go back through loads of past papers, you can find all sorts of different questions on moles. So yeah, definitely A-level questions. It doesn't feel like it because it feels comparatively simple, but if we don't have these simple bits nailed, when you get those horrible questions like the one that we just did in part 1, the end of part 1, if you don't have the simpler bits, I know none of it's simple, is it? But the simpler bits nailed, then we find the harder bits even harder. So super quickly, how do we do this then? If we've got 0.8 moles per decimeter cubed of sodium carbonate, it reacts with 12 grams of potassium fluoride. Calculate the reacting volume of sodium carbonate. Well, we're going to need our moles of potassium fluoride first. Whenever you've got a formula and a mass, you can always work out the moles because we can work out the MR. Yeah, brilliant, Team Echo, exactly right. So we need to work out the MR of potassium fluoride. Potassium is, I can't remember what, fluorine is 19 point or just under 19, isn't it? So my MR is going to be I've got 58.1 written in front of me, so let me know if you've got something different. 39, it is 39. Okay, lovely. So 39 plus 19.1 or whatever it is. Brilliant. So 58.1, perfect. And then moles, therefore, is mass divided by MR. So our moles of potassium fluoride, lovely, is 12 grams divided by 58.1 grams per mole, gives us 0.206 moles of potassium fluoride. Oh, not of FF, of KF. Lovely. And then now what do we do? So we know how many moles of potassium fluoride we've got. So Mashafi, I don't know if you were here for the end of part 1, but if you scroll back to the final exam question on our PowerPoint, that was nice and challenging. It was a good, nicely challenging one. And there is a I don't think it's that much harder actually. There is a harder question coming up, which we won't have to ratio. So if we've got 0.26 moles of KF, we must have half as many of our sodium carbonate, moles of NaCO3. There's got to be half the moles of KF. Good. And then we've got to work out our volume by doing, yeah, good, lovely. That looks great. So what is that? 0.103. That's our moles of sodium carbonate. And then our volume, again, we're going to need to rearrange the equation. So volume equals moles divided by concentration, as long as we are paying attention to what our units are. So here our concentration is given in moles per decimeter cubed. So because our concentration is given in moles per decimeter cubed, we don't actually need to do the 1,000. Yeah, well done. Good, you spotted it first. Brilliant. Absolutely perfect. So 0.103 moles divided by my concentration, which is 0.8 moles per decimeter cubed. I've slightly run out of space, apologies. So my volume should be, my volume of sodium carbonate, is 0.129 decimeters cubed to 3 sig figs. Phew. Very nice. Well done. Okay. So I appreciate that these might not be as hard for some people, but if we don't get them right, we are stuck. And in the heat of an exam, sometimes we forget these simpler ones. Sometimes we forget that we do know the equation moles equals conc times volume. Or, you know, we do know moles equals mass over MR, and we forget. So it's always worth practicing these sorts of questions. I'm just going to skip that for now, but please do make sure that you've worked out how confident you feel about doing those kind of questions. And I'm just going to give you the answer that I have written down here. So we're asked to find the concentration of phosphoric acid to 3 sig figs. So I have got a value of 1.23 moles per decimeter cubed. So please feel free to go through and check if you can do that question. And there's the answer for you to check as well. Is 3 sig figs always needed? No, that's a very good question, actually. It entirely depends what's given in your exam question. So here they've been really nice and they've asked you specifically to give it in 3 to 3 significant figures. However, they may not always. They may say give it to an appropriate number of significant figures, which would be mean, but they can do that. If they do, then look at how many significant figures than have been given in the question. And actually, you have to take the fewest number of significant figures given, and that is as many as you can give. So in this case, both those numbers are given to 3 significant figures, so that would make sense for us to give our answer to 3 significant figures, but it's always worth checking, especially if they ask you for an appropriate number of significant figures, because then they're trying to trip us up. Okay, yeah, cool, brilliant, well done, guys. Yes, I know what you mean, Timaku. It's for me, I was the same. It's much easier, or to begin with, I think it's really useful to practice with somebody who can help you talk through the process, because once you've done a few of them and you've practiced a few of them, same, all these different questions, and you get used to, oh, I do that, and then I can work out that, and then I can work out that, done. So yeah, always useful. Awesome. So we've looked at the formula linking moles, conc, and volume. We've performed some calculations using it, and we've performed calculations using mass and concentration. Please feel free to have a go at that last exam question, which we didn't get through. But if you have any questions for me, then please let me know. Otherwise, we haven't got our next YouTube classes scheduled. There will be some more coming up, so please keep an eye out on our YouTube schedule for some more free classes. You're absolutely welcome, and I'll hopefully see you in September. There will be one in September, and hopefully see you then. Oh, well, you're very welcome, Timaku. I'm not 100% sure, actually. If you send an email to the email address hello@snaprevise.co.uk. Oh, that was a funny one. snaprevise.co.uk, and have a chat with the person on the end of the email. They may be able to advise you about what is possible or what is available. I actually don't know, so I'm the wrong person to ask, I'm afraid. But if you drop that email address, hello, HELLO, @snaprevise.co.uk, if you drop them an email, you could, they may be able to help you with that. Okay. Lovely. Well, thanks, guys. You've been brilliant. Really useful. Or I think it's much more useful for you guys when you're interactive. So really well done and fantastic. And I hope to see you at a future web class. Thank you very much, guys. Bye.